Hello, today we're going to look at vectors and dot product. The dot product is vector multiplication. The answer is going to be a scalar. That's going to be just a number. So if you look up at the formula up here for dot product, u dot v is going to be u1 v1 plus u2 v2. So how this is going to work, let's look at example 1 and we'll try this one together. It's very simple. So if we take the dot product of these two vectors in component form, then our answer is going to be 5 times 3. This would be u1, u2, v1, v2. So we have vector u and vector v. The solution is going to be 5 times 3 plus -2 times 4. So the dot product is going to be 15 subtract 8, which equals 7. Example 2, properties of dot product. The properties of dot product are the same as number 1, commutative property, u dot v equals v dot u. Number 2, you can see u dot u is equal to the magnitude of u squared. Number 3, 0 dot u equals 0, zero product property. Number 4 is the distributive property. And number 5 is the associative property. Looking at example 2, we're going to start with w dot w. So if you look at what vector w is, it's 5, -2. So we're going to do 5, -2 dot 5, -2. So according to dot property, this is going to give you 5 times 5 plus -2 times -2, and that's going to equal 29. Okay, the magnitude of w squared. So we're going to show, we're looking at number 2, and we're showing that the left side, w dot w, is equivalent to the magnitude of w squared. So let's look at what the magnitude of w squared is equal to. It should give us 29 again, correct? So we take the same vector, and this time we're going to find the magnitude of it. So to find the magnitude of vector w, you're going to do the square root of 5 squared plus -2 squared. And that's going to give us the magnitude. So that's going to be the square root of 29. And now we want to take the magnitude and we want to square it. So we're going to take that value and square it, and it's going to give us 29. Therefore, A equals B in those two examples, proving number 2. All right, the next one we're going to do is look at C and D. C and D is going to show us how number 4 is equivalent. So looking at C, we have V plus W. So when you're adding vectors, you would start with vector V, which is 1, 0, and you're going to add that to vector W, which is 5, -2. So that's going to give us a vector, and we're going to add the horizontal components together, which is 1 plus 5, so that equals 6. And then we're going to add the vertical components together, 0 plus -2, and that's going to give us -2. Now what we're going to do is we're going to take that and do the dot product of vector u. And vector u happens to be -3, 6. So calculate the dot product of that. It's going to be 6 times -3 plus -2 times, let's see, 6 times -3 plus -2 times 6. So that's -18 minus 12. -18 subtract 12. and that's going to give me negative 30. So on number 4, we just did this side. Now we're going to prove that it's equivalent to u dot v plus u dot w. So looking at our problem, it would be v dot u plus w dot u. So looking at that, let's take v dot u first. So v dot u is, vector v is 1, 0, dot, and vector u is negative 3, 6. So when I take the dot product of that, I'm going to get 1 times negative 3, which is negative 3, and 0 times 6, which is 0, and that's going to give me negative 3. I'm going to take that negative 3 and I'm going to add it to the dot product of w dot u. So w is 5, negative 2, dot u, which is negative 3, 6. So let's take the dot product of that. That's going to, now we'll take the dot product of w dot u. So that's going to give us 5 times negative 3, which is negative 15, plus negative 2 times 6, which is negative 12. And negative 15 and negative 12 is negative 27. We're going to add those two dot products together. So negative 3 plus negative 27 equals negative 30. So you can see that the left side on number 4 was equal to the right side. To find the angle between two vectors, you use this formula right here. Theta is going to be equal to the inverse cosine of u dot v over the magnitude of u, magnitude of v. If you want to see the proof for that formula, it is on page 133, and you use the law of cosines to derive that formula. In this example, we're going to use the formula to find u dot v with the given information. So looking to find u dot v, we're going to start with the cosine of theta, and theta is given, it's 5 pi over 6, is equal to u dot v, that's what we're solving for, over the magnitude of u, that's 6, times the magnitude of v, which is 8. So now we're just going to simplify this. We know what the cosine of 5 pi over 6 is. We're in the second quadrant. The reference angle is pi over 6. So that's going to give us negative root 3 over 2, since we're in the second, equals u dot v over 48. Again, all we're doing is trying to solve for u dot v. So we'll multiply 48 to the other side. And so u dot v is going to equal, we can go ahead and simplify this. 2 goes into 48 24 times. And that's going to give us negative 24 square root of 3. In example 4, we're going to find angle A. In order to find angle A, the first thing we're going to have to do is find the magnitude of the vector AB and the vector AC. So in order to do that, we're going to have to first put them in component form. So we're going to do vector AB, and we learned this in section 6.3, and we're going to put this vector in component form. To do that, it's x2 minus x1, so this is going to be 4 subtract 3, and then y2 minus y1, 2 subtract 0. Because we care about the direction, when you're putting it in component form, you always start on the terminal side and you subtract the initial side, and that will give you the right direction. So this vector in component form is going to be 1, 2. Now we'll find the length or the magnitude of that vector. So the magnitude of vector AB is going to equal the square root of 1 squared plus 2 squared. This is going to give me the square root of 5. Now we're going to find the component form of vector AC. So looking at this, we're going to do AC, and we're going to do the same thing we did to find the component form of vector AB. We're going to do x2 subtract x1, so 5 subtract 3. And then y2, which is 1, subtract 0. The component form of that vector is going to be 2, 1. You'll see that when we try to find the magnitude of that vector, the magnitude of that vector is going to end up being the same as the other one. So because we're going to have 2 squared plus 1 squared, which is the square root of 5. So the magnitude of both of these vectors is root 5. Now that we know the magnitude, we can come up top and we can use the formula to find the angle in between those two vectors. Now we'll find theta. To find theta, theta is equal to the inverse cosine of u dot v. So that's going to be 2, 1 dot 1, 2 over the magnitude of AB, which is root 5, times the magnitude of AC, which is root 5. It's the magnitude of the two sides that the angle is in between. All right, dot product. So you'll do 2 times 1 plus 1 times 2. So that's going to be 2 plus 2, which is 4. And root 5 times root 5, which is 5. Theta is going to equal the inverse cosine of 4/5. You put that into your calculator, you're in degree mode, and you get 36.870 degrees. That's the angle, theta right here, in between vector AB and AC.
Orthogonal vectors. So orthogonal vectors are two vectors who form a 90-degree angle. So basically they're perpendicular. How you can tell if they're orthogonal or perpendicular is their dot product is going to be equal to 0, or the angle between the two non-zero orthogonal vectors is 90 degrees. Now, parallel vectors are going to be if the cosine of theta is equal to -1. Remember that we're asking which angle, where is theta when the cosine is equal to -1 or +1? And we're looking at 0 degrees, 180 degrees, or back around at 360 again. So the cosine of theta, how do we find the cosine of theta? We use u dot v divided by the magnitude of u, magnitude of v, and that must be equal to 1 or -1, and then I would have parallel vectors. So let's start with example 5a. Are the vectors orthogonal, parallel, or neither? So the very first test I look for is orthogonal because that's the easiest. If I take vector v, I'm going to write it in component form. So 3, -2. And vector w is going to be 3, 4. So let's go ahead and find v dot w. So v dot w is 3 times 3 is 9, plus -2 times 4 is -8, and that equals 1. Well, I was looking for this to equal 0 in order for it to be orthogonal. So is it orthogonal? The answer is no, it's not. All right, so now we're going to test to see if it's parallel. So to test if it's parallel, we need to take the cosine of theta has to be equal to -1 or 1. So this is going to be the cosine of theta. How you find that is u dot v over the magnitude of u times the magnitude of V. So let's come over here and find the magnitude. The magnitude of V is going to be the square root of 3 squared plus negative 2 squared, which is the square root of 9 plus 4, which is the square root of 13. The magnitude of W is equal to the square root of, and you just use Pythagorean, so 3 squared plus 4 squared. So it's a squared plus b squared. And the magnitude of W equals the square root of 9 plus 16, which is the square root of 25, which equals 5. So now U dot V, we already did U dot V over here, and U dot V in this formula, it's actually going to be V dot W. So I can rewrite this if you want. So V dot W over the magnitude of V times the magnitude of W, just so we have the same variables. So V dot W is 1. And then the magnitude of V was root 13, and the magnitude of W was times 5. Well, that does not equal 1 or negative 1. So you're looking for 1 or negative 1. So therefore, it's not parallel either. So my answer is these vectors are neither. So go ahead and stop the video, try B, and then you can test to see if it's orthogonal, if it's parallel, or if it's neither. So looking at orthogonal, it's going to be V dot W, and V dot W is going to be 3 times 4 plus negative 2 times 6. So this is just dot product. So 12 plus a negative 12 is equal to 0. Because the dot product is 0, then we know that the vectors are orthogonal. So the next thing we're going to look at is vector projection. So the vector projection is where you take one vector and you project it onto another. So the projection of U onto V. So here's vector U, and we're going to project it onto this surface here, which is vector V. I like to think of it as, so if you had a sun here, and this vector here, U, is projecting this shadow down here onto vector V. And so the formula for this is right here. Notice that the larger vector is U is projected onto the dropped vector V. So this is the projection of U onto V is going to be U dot V divided by the magnitude of V squared times vector V. So again, V is the vector that U is projecting onto. So you can project force, you can project magnitude all onto this vector. Example 6, find the projection of V onto W. So you can see here's the projection of V onto W. And we're going to do that by doing V dot W over the magnitude of W squared times vector W. Now in physics, you see problems like with carts here, and we're looking for the vector that's going to stop the cart from rolling down the hill. So it's this force vector that's moving upward, which you have a vector moving downward in the same magnitude. So projection vectors, you can see that this forms a right triangle, and what I can do is I can use Sohcahtoa as well as this projection formula. So I'm going to show you how to use both. So looking at the formula, we're just going to simply plug in V dot W. So V dot W is, ooh, that's really thick. Let's erase that. So V dot W is going to be where you have 1 times 1 is 1, plus 3 times 1 is 3, And so v dot w is equal to 4. So the numerator is going to be 4. And then the denominator is going to be the magnitude of w. So the magnitude of vector w is going to be the square root of a squared plus b squared. So 1 squared plus 1 squared. So the magnitude of w is going to be the square root of 2. So I have v dot w on top. I have the square root of 2, which is the magnitude of w, and then you square it. And then this is going to be multiplied by vector w, which is 1, 1. So let's go ahead and simplify this a little bit. You can see that the square and the square root are going to cancel. 2 divides into 4 2 times. So this is a scalar. 2 times vector 1, 1 is going to be 2, 2. So the projection vector is going to end up being 2, 2, the projection of v onto w. Now the question says, write vector v, here's vector v, as the sum of 2 orthogonal vectors. All right, so if you look up here, you can see here that u1 plus u2 is going to give me the resultant vector of u, right? So u2 is equal to, so again, if I wrote it as u1 plus u2 is equal to vector u, then u2, which is this perpendicular vector, is going to equal u subtract u1. So we're going to figure out what these two vectors are when we add them together to get this orthogonal vector, which is going to form 90 degrees. All right, so in order to do that, we are going to take vector v, which is 1, 3, and we're going to subtract the projection vector, which is 2, 2. And that gives me 1 subtract 2 is negative 1, and 3 subtract 2 is 1. So what this means then is negative 1, 1 plus the projection vector 2, 2 should equal vector v, which is 1, 3. So let's check. Negative 1 plus 2 is 1, and 1 plus 2 is 3. And so here I just wrote vector v. Here's vector v. And I wrote it as the sum of 2 orthogonal vectors. Now, how would I prove that these two vectors are orthogonal? That means their dot product should give me 0. Let's try. So negative 1 times 2. So multiply the x component, or the horizontal component, plus 1 times 2. And notice that this gives me negative 2 plus 2, which equals 0. Check. These two vectors are orthogonal. And they're the sum of vector v. So looking at example 7, we're going to look at the classic physics problem where you have a cart and you want to keep that 200-pound cart from rolling down a 30-degree incline. And so we're looking for this force vector here to keep that cart from rolling down. So how we're going to do that is we're going to form a triangle, and you can use the projection vector if you would like, where you project vector g onto vector v, or there's an easier way to do it, and that's just to form a right triangle. So I'm going to take this triangle right here, and I'm going to bring it over here. So what I have is I have the cart. So this is the force of the cart, which is 200 pounds. And then I have a gravity force. So here is my gravity force. And then with my gravity force, I have this force here that's keeping the cart F from rolling down the ramp. So this question is asking me to find F. And so this is a right triangle here. And what we're going to do is we're going to use Sohcahtoa. And the really nice thing is by looking at triangles, if this is 30 degrees, then we know this angle here between the gravity and the force of the cart, or how much the cart weighs, is going to be 30 degrees. Ooh, that looks like 300. Darn it, 30 degrees. So this is 30 degrees here. And then because this is a right triangle, we can use Sohcahtoa to figure out what side F is, and that's going to be the force. So just use Sohcahtoa. I think that's much easier than this projection formula. I wanted to introduce you to the projection formula in case you end up in a higher level math class and you see it again. So this is going to be, I'm looking for the opposite, so I'm going to use sine. So the sine of 30 degrees is equal to the opposite, F, over the hypotenuse, which is 200. So 200 sine of 30 degrees is equal to F. Now, I know what the sine of 30 degrees is. It's 1/2. So I don't need a calculator on this one. 200 times 1/2 is the force. So I need a 100-pound force to keep that cart from rolling down this hill. Now, if I were looking for what the gravity vector is, then I could simply use cosine, because in comparison to this 30 degrees, this would be the adjacent side. So I could do the cosine of 30 degrees is equal to G over 200. And then I could go from there. The cosine of 30 degrees is √3/2. So this would be 200 times √3/2 is the gravity vector. And then this goes in 100 times. So the gravity vector is 100 √3. All right, so you're going to do one of these on Alex, and I would just use the right triangle instead of the projection vector. Okay, last problem is a work problem. So we are going to look at work. We have a person who pulls a wagon with a constant force of 15 pounds at a constant angle of 40 degrees, and they pull it for 500 feet. So what is the person's work? So looking at that, you're simply going to just use this work formula, which is really, really easy to use. So the work is going to equal the cosine of the angle. So you can see it's right here. So you would do the cosine of 40 degrees, and that is not special, so I'd throw it in my calculator. And then you're going to times that by the force of the 15 pounds, and then the distance of the 500 feet. You simply throw that all into your calculator. And these are called foot pounds. Your answer is in foot pounds or joules. And you're going to end up with 5,745.333 foot pounds. So try the U-try and try the reflection, and that's everything for 6.4.